Hi everyone, my name is Dhairya Gandhi. Welcome to the talk. And this talk is largely going to be about how Flux has progressed over the past year, along with all the different tooling that goes along with it, be it the AD or the external things or the performance tuning, all of that. We will touch upon different ways Flux interacts with the larger ecosystem within Julia and even beyond. We will talk about some of the awesome work that has been produced recently by the great community that we have, including even GSOC students, both past and current. And yeah, let's dive in. So I wanted to start by talking about how Flux has responded to the way basically the entire machine learning story has progressed in a more general sense. And one really interesting advancement and development has been the marked shift in research that is using machine learning as part of scientific software. So with neural ODEs a couple of years ago, it was showed that it was in fact possible to use neural networks to replace parts of a system of an entirely scientific system to accelerate those models by thousands of times. That was thanks to not having to do a lot of the computation simply, and because neural networks were cheaper to train, it opened up the possibility of having a completely universal differential equations system where you could also have these neural networks partake in and basically approximate dynamics of systems that were not known previously. So with this, it really showed the need for a truly differentiable language. And Zygote then came up as a very capable AD engine with the potential to act as the mediator between high performance differentiable code with little more than the language itself versus all the code that the users could throw at it basically. So our goal with Zygote was always to make an entirely differentiable language. We demonstrated that earlier with Defeat Flux, Chris Rackauckus and differential equations with his team along with Flux. We brought together this entire ecosystem where it was in fact possible to write completely universal neural differential equations. And it was used in a vast array of really interesting problems in very different domains. Um, and this is just a demonstration of a simple Lotka-Volterra system, but in this journey, what we really understood was that scientific systems are written very differently from your average neural network. Um, the high point being that machine learning softwares are usually restricted to some of these frameworks that are out there, which are popular. And it means that they're very high level, they are flexible, but it also means that the programs that they produce are generally very simple. So, for example, an MLP or a convolution is vastly more different than an actual differential equation solver. Another thing that really happened in this whole journey was we understood that not only do machine learning stacks not deal with performance tuning to the point of scientific systems do, they also require a lot more of the host languages features that they use to actually scale out or get performance or actually solve problems. So this could be anything from parallelization to vectorization, checkpointing, what have you. So a vast majority of this overhead basically meant that it was the AD engine basically that needed to support all of the host languages semantics, because not only are you now expected to differentiate through a neural network or a chain, you are now expected to differentiate through this entire rich ecosystem of differential equation solvers, right? And scientific solvers, which by themselves are using a vast different kinds of tooling and semantics to actually solve their problems, which also meant that all library code now must be considered at par with the host language code. So be that with custom types, be that with you know, recursions, control flows, all of that needs to be supported. Not only that, parallelism is something that came up quite frequently because a lot of scientific software relies on its parallel nature to actually scale out to a large amount of compute. But all of this serves to show that there are some very, very, major hurdles that are come our way. So languages are varied and their semantics are usually very hard to reason about. Julia has a lot of features that we as developers really, really love, be that multiple dispatch, be that the type system, broadcasting, so on. Its performance for sure. Um, and what it really means is that for us to be considered a properly differentiable language, we must do this without compromising on the performance. So not only does Flux and Zygote therefore support programming primitives like control flow and recursion, dynamic dispatch, etc., it also has to support features that the language is actively developing on and users out there are actively looking to take advantage of them. So that can be things like threading, parallelism, etc. One interesting thing to note here is that this means that not all code will always be differentiable. What does it exactly mean to differentiate a bunch of threads, right? So how does an AD engine is expected to solve that? So it's done in a very simple, principled manner. We don't really expect Zygote to differentiate everything, but what we do expect Zygote to do is basically use what it knows, its primitives, and then use it to construct the pullback in a manner that generates the correct gradients for all the functions that we are interested in. And one very crucial way this is done is through the use of pullbacks. So now, as you can see, regarding, I would rather not define an adjoint for my function foo here, but I do want to teach Zygote how to differentiate through bar and bars. And once I do that, it is actually completely plausible for me to, just stack up all of these different pullbacks and construct them back into in the same manner as they were outputted in the first place to generate my gradients completely seamlessly. Now, this means that I have given my users complete control of what happens in the backwards pass. Why? Because now I can write my own adjoint using the adjoint macro that Zygote exposes, which can be used to play around with all of these specific tools. This really does mean that Zygote transitions from being an automatic differentiation engine to more of a tooling required to make an entire language differentiable. So this is an example of how a PMAP system would work, right? So this is data parallelism essentially across multiple workers. Uh, so here, this might not be super common in machine learning, not at least until we actually try to work with uh, you know scaled out training and such. But in scientific software, it's fairly common. And what we really see here is that all we do is that we say, okay, fine, give me the pullbacks of all the little on all the workers, and then in my backwards pass, parallelize that as well and return back the results. That's really all there is to it. What this means is that with just 8 lines of very simple code without any real adjoints or any maths anywhere, we're able to differentiate across multiple workers very, very simply. So of course, this is a very simple example, but this is completely generalizable and it can add without adding to the complexity to the user's end. They can simply just PMAP things and expect it to work now out of the box. One other thing that we alluded to before was that scientific compute really requires, a different idea of how much scalar operations are used at a large scale, right? And Zygote has so far been a reverse mode AD engine because we've been interested in the backpropagation for our neural networks. However, in many cases, forward mode has great advantages to give, especially in terms of scalar code. And code that is actually efficient on scalar mode can easily be annotated as such so that whenever people want to use a part of their code in a very scalar fashion, they can just annotate it to use the forward mode rather than the usual reverse mode. This increases our performance capacity as well as meaning that we can support a much more vast array of problems. So here I am announcing the basic release of the Zygote's forward mode, and it's available to you as of Zygote 0.5. You just have to using Zygote.forward. Um, so in here, I'm taking a simple example of creating a dense layer, which is how one would typically solve for an MLP in MNIST, for example. And one simple thing that we see here is that you just have to call on Zygote the push forward function, and initial benchmarking shows that even though it's early days, it can really hold its own against more robust AD engines of that have existed in the Julia ecosystem before, and we see about a 10x speed up, which is really exciting. The forward mode still has some extra overhead in much smaller problems, but on real world use cases like this, it should technically outperform the existing solutions by quite a much. So this has just been the very tip of the iceberg, right? And there's a lot more to consider here. And I wanted to talk a little bit about some of the more new features in Flux that our community as well as the developers have put a lot of work into producing for making Flux into a more easily accessible ecosystem. Now, one of them is just the data loaders, right? So previously we were used to writing these iterables which we would have to feed into the train function. However, it meant that we had to really understand what was happening inside the train function to write the data loader properly. However, that is changing now. We're used to this basic idea that anytime we want to solve anything, the mini batch has to respond with the data and the labels and the corresponding labels. Well, here you have the same basic API where you give it a tuple of x and y, but this is in this case is just all of the data. In other cases, you can expect this to be lace loaded data, loaded into channels and loaded from memory efficiently, things like that. And that's all that there is to it really. And you can specify all kinds of different things within the data loaders to make it easier to begin with, right? We also noticed that users had some real difficulty finding these, little things that makes Flux that much more friendly to use, which were using custom arrays as weights and biases, for which we introduced these core-only constructors. So it's easier for people to basically suggest to Flux to use a particular array that could be through uh, for whatever reason that's required. We also came up with these functional optimizers, and these are really interesting because they allow us to be a lot more flexible within the training routines that we have, and it also provides a much more functional API towards the optimizers that have been written so far. Further, it means that these are very friendly with compilers like XLA, which means that we can see a lot more of this heavy rearrangement that these compilers can do to eke out as much performance from our algorithms as we want, basically. It also provides a much more principled approach to how our optimization routine interacts with the modeling itself. So recently, through a lot of community efforts, along with the GitHub MLH, the Major League Hacking System, we also got a lot of students interested, and they added in some of the pooling layers which were requested for often. So this means that adaptive and global pooling layers are now part of the Flux API. Another thing that we, were asked for often was, this bias switch to turn off biases for different kinds of modeling. Now, this could have been done through a very simple quirk which said bias equals false, But we went ahead and did it in a manner which was completely generic and exposed it so that it's easy for people to use nonetheless, which means that it can be used across different layers, and it's Zygote aware, which means that at any point in time, Zygote will know how to deal with it, to leave it alone and not train it basically. So it makes it really easy to not have to write any hacky code if one wanted to say match an implementation or reproduce a paper or whatever. So yeah. Another interesting bit of progress has been the adoption of chain rules support into Zygote. So chain rules aims to provide these adjoint definitions for a lot of these common operations in a formalized AD language, which means that we don't really need to maintain these adjoints inside Zygote anymore. And as a matter of fact, we can share these adjoints with the rest of the ecosystem in a much more feasible manner. Chain rules have support for both forward mode and reverse mode, which means that we can realistically see forward mode and reverse mode, mixed mode AD become significantly more easier to adopt for newer AD engines that might want to take advantage of them and have those rules defined just by consuming the chain rules API. Another really interesting piece of development has been in the vectorization support. So vectorization is again something that has been used in many cases, especially where those instructions are available to speed up computations on the CPU. And even though it's a little bit early days, we're testing and validating that we can provide these fairly transparently via loop vectorization.jl. Um, the initial results seem to suggest that in some use cases, we can expect to see up to 5x performance on the same CPUs as previously. So that's really exciting. But this is just a very, very small list of the things that I have time to talk about because I really want to touch upon the incredible community that Flux has going about it, and makes me really thankful to be a part of this really amazing group of people who are so dedicated towards what they do. And it makes the entire ecosystem that much more of a joy to use, really. So let me start off with Mike Innes's XLA.jl. This brings the XLA backend to Flux, which means that we can do a lot more of this rearrangement in a completely functional manner, so that we can actually rearrange our computations in a manner which will be able to reuse memory, do more efficient caching, and in general increase our throughput and bring us basically at par with what TensorFlow has already put into the research and development of their XLA backend. And the API for that is very, very minimal. It's literally just calling XLA of the function that we want to move to XLA, which is in this case our forward mode, backwards mode, and our optimizer. So this would also give us an opportunity to use our functional optimizers. And it means that not only will this allow us to use Flux on hardwares like TPUs much more readily, but it also means that we are getting a huge speed up, almost on the order of a magnitude in many cases. So another area of inquiry was that we saw that there was a real need for us to basically be able to see how we're progressing in against the rest of the ecosystem, as well as provide these PyTorch kernels to the users who need it most. So for example, on things like ResNet and Inception, where we have optimized kernels already available in Torch, it makes sense to also have these available in Julia through Flux. And this is so that people don't really have to make any compromise in terms of performance when they're training their models with, and also have the flexibility. So this is done in a manner which can take as much responsibility of the flexibility from the toss tensors behaving as much like Julia arrays as they can, and also shows that it brings up about a 3 to 4x speed up on the forward pass as well as much more on the backwards pass as well. So we also saw this as an opportunity to make it so that it was possible to translate models from PyTorch to Flux really quickly, especially even with pre-trained models. So giving this kind of tooling makes it easier for people to try out our ecosystem as well. AlphaZero.jl by Jonathan Laurent has been one of the most interesting projects recently that we've seen, and it implements a generic AlphaZero that DeepMind produced, and it's done in a very simple manner so that it's easier for people to approach. And it also served to test out how Flux can scale up. And this is a very large resource hungry algorithm, and it demonstrated that Flux can take advantage of a lot more compute as much as we can give it, really. And it served out to test the algorithms on newer use cases, for example Connect 4, like we can see in this chart here. Object-detector.jl has been another one of those packages which brings state-of-the-art YOLO models to Julia and Flux. And YOLO is a very popular class of object detection models known for its high throughput and high performance. And these benchmarks actually go on to show that we can actually outperform the numbers put on by darknet on the same hardware as well, which is really exciting for us. I also want to take this opportunity to talk about some of the GSOC work that has gone over the past few months, and it really goes on to show, how easy our tooling can be if we can have, Nirmal, who has been one of our GSOC students, to take over, things like Zygote and actually use it to translate over, differentiable 3D data to be trained using Flux. And this is meant to, work with and manipulate, different kinds of 3D meshes, point clouds, voxels, what have you. It packages together different, of these functionalities so that we can basically have efficient supervised learning on 3D point cloud data. In fact, some of the benchmarking that we did earlier showed that it can actually outperform state-of-the-art tooling for the same work like Kaolin by about 3x, which is really exciting as well. Transformers.hugging face is another project that came out of our GSOC ventures. Peter Cheng is the author behind it. And this has been his second GSOC, and it basically aims to bring high quality pre-trained transformer models to everyone in Julia. It also means that it vastly increases our capacity to natural language understanding and natural language generation tasks, and it makes it easily available to anyone who really needs it. Um, this we believe is very important since it reduces the friction basically that is present in working with such large models at the edge of research. Another really cool project that is coming up is the Fast AI port to Julia. So this has been taken over by Kyle and Brian and others to basically, bring up the port of the Fast AI, library v2 API to Julia and make it compatible with Flux in a manner, which reduces the amount of friction again for a newcomer, so that we have very highly abstracted out routines, which don't take away from all the flexibility that Flux provides, but also rather adds to making it easier for people to have a more complete experience. This is still a work in progress, but it is really exciting nonetheless. So another thing that I wanted to touch on is how Zygote has been adopted in the larger ecosystem. And a quick search on Julia Hub shows that Zygote has a combined almost 90 dependencies across both direct and indirect reverse dependencies, which means that a lot more people are taking Zygote as a part of their modeling story and a part of their development story, which means that we can expect to see a lot more of the larger ecosystem to be completely differentiable as well. This is not in no short form thanks to the amazing community that has made all of this tooling possible through contributing code, benchmarks, issues, talks, what have you. So this could not have been done individually for sure, and this number of contributors is not representative of the actual larger community that has come together, banded together to produce such an exciting ecosystem where we have both traditional as well as very forward-looking, methods of inquiry, and it makes me so happy to be part of such a team. Thank you so much, and I'm very excited to see how folks play with all the tooling that we've developed so far, and what the next stage of it brings us. Thank you.